It's my great pleasure to introduce David Lacoste from he's research director at the Gulliver Laboratory at CNRS in Paris. Just before we started, please everyone mute and submit questions on the chat. We might ask a few during the talk if it's okay with David, and then we can also have a more open discussion afterwards. Yeah, so just very briefly about David's CV. He habilitated at the University of Pierre and Marie Curie in Paris. He has a PhD in theoretical physics, and he worked from the Joseph Fourier University in Grenoble. And he has a broad interest in soft matter physics and non-equilibrium statistical mechanics. And yeah, today he is going to speak about the emergence of homochirality in large molecular systems. It's a great pleasure to have him here. I'm very excited. Thank you for being here. He's very tired. He said he came from Japan, but he made time to be here. Okay, over to you, David.
Okay, thank you very much for this kind of introduction. Yeah, I may not be completely sharp, but I'll do my best. And please interrupt me anytime if there are questions. Okay, so today I want to tell you about the homochirality of living matter, basically, and this is a talk that will be divided in 3 parts. So in the first part, I will explain what is autocatalysis, and this is a joint project with Philippe Enguet, who is a colleague of mine at ESPCI in Paris, and the work was also done by Alex Bloch, who is a PhD student. So, and once we know what autocatalysis is, we will then turn to the main part of the talk, which is about homochirality, and then I'll present a scenario to explain how homochirality can emerge in large molecular systems, and this is a collaboration with Pierre Gaspard from Brussels University, and the work is done by a different PhD student, Gabin Laurent. And then in the third part, I will explain a scenario that links homochirality with the emergence of the first polymers. And there it's a joint work with the Munich University, in particular, Tobias Göppel and Ulrich Gerland. Okay, so what is autocatalysis? So to answer this question, we went back to the actual official definition from the EU PAC, which is the authority in chemistry. And there you can read that a catalyst is a substance that increases the rate of reaction without modifying the overall standard Gibbs energy change. It's both a reactant and product of the reaction, and catalysis brought by one of the products is called autocatalysis. So in this definition, autocatalysis is a special case of catalysis, and for that reason we kind of forge a new term to make the distinction between the catalysis, which is not autocatalysis, and we call that allocatalysis. So to distinguish the two, you have on this simple table, you see what you can do. You can ask a simple question like, is there any species that is both reactant and product? If the answer is yes, then you are in either in autocatalysis or allocatalysis. And then to distinguish the two, you need to look if there is a species that is produced in the net reaction. And that's, in this case, you would see that, for instance, in the first case, B is produced, and so you have autocatalysis, whereas in the second case, you don't. So anyway, so this looks very elementary, but in fact, it's possible to make this a bit more precise, to analyze in particular the criterion that one can build at the level of a stoichiometric matrix to define what autocatalysis is. And this mathematical conditions amounts to basically finding a submatrix of the stoichiometric matrix, which has certain very specific properties. So here on this diagram, for instance, I distinguish in blue species which are sort of fuel molecule, and from species in yellow, which are the autocatalysts themselves. And on the right here, you have, I hope you can see my mouse, you have a hypergraph representation of this simple two case of allocatalysis and autocatalysis. So once you have this property mathematically defined, you can use them to, in fact, identify specific motifs that need to be present in every autocatalytic network of reactions. And we found that, in fact, there are only a few of these motifs. We found 5 types, and you can see them represented here again in a hypergraph representation, which is a bit simplified, but which is useful to represent these 5 types. So, for instance, I will not go into the details because this would be for a different talk. But in the type 1, you have, for instance, this famous Formose reaction, where you start with a molecule which has a 2 carbon atom, and you add progressively formaldehyde, which contains only 1 carbon atom, and you go from in this way from C2 to C3. Then you can have C3 prime, C4 prime, C4, and then when you add C4, you have a fork that makes twice a molecule with 2 carbon atoms. And so in this way, you see this in type 1, you have just a simple cycle, which and only 1 fork essentially in the structure. Then you can go on. The topology is changing a little bit as you change the type. But what is interesting is that you can recognize these motifs overall in chemistry, even in complex networks such as the Krebs cycle. You can recognize this structure. So this is a stoichiometric characterization only, so it doesn't tell you that this structure can be dynamically realized. Nevertheless, we have studied the connection between dynamical threshold, above which autocatalysis is possible, and the topology as characterized by the different types that I told you about. And so we found that indeed, for instance, if you look at this probability of extinction as function of this parameter xi, you see that this probability depends on this parameter. So let me explain. So probability of extinction, that means that you put 1 molecule in the autocatalytic cycle, and you ask, does this molecule is this molecule able to reproduce itself or to grow in number in running the cycle? So if the answer is yes, you're above the threshold of autocatalysis. And what you see in this graph is that this threshold actually depends on this parameter psi, which in fact is called the specificity of the reaction in the cycle. So there is a link between the dynamical characterization and the stoichiometric characterization. And the other point that we've made in that work, and I'm just going to finish with that on the autocatalysis, is the point that there are in fact more forms of autocatalysis than one would think naively. Namely that there are forms of autocatalysis which involves multiple compartments, and that means that essentially, if you didn't have the compartments, you wouldn't have the autocatalysis. This form of autocatalysis is possible only because you have several compartments. So this is illustrated in these little cartoons where you have separately these two reactions, and then you have these membranes that can let some species go through. And because of this membrane, and because of the fact that you have these two cycles, you can have globally something autocatalytic. Okay, so this was it for autocatalysis. I hope this this was clear. This is a bit fast because I want to go to the meat of the talk, which is the homochirality of life. Everything's fine so far? Okay, well.
Can you hear us?
Yes?
You can hear us, David. Okay, because we have some system set up here. Okay, cool. No, it's good.
It's good? Okay. Yeah, I'm sorry because I'm in full screen, so I'm not seeing you. If I go out of full screen, so I'm not seeing anything basically. I'm just giving the presentation, but that's fine. If you hear me, it's fine. So I'll go now to the second part, which is what is homochirality of life. So the homochirality of life means the absolute dominance of one enantiomer in the pair of two molecules that you have with chiral molecules. So basically, chiral molecules come in pairs. You have two pairs, pair of enantiomers. And what is striking in living matter is that whatever the molecule, you always have only one of the two enantiomers. And for instance, you have 21 amino acids, and they are essentially all L enantiomers except for one, which is achiral. Same thing for sugars; they are all D enantiomers. Same thing at higher lengths, at higher scale. You have DNA molecules which are right-handed, RNA molecules are left-handed, and in fact, we have known this for a long time, and there's not a very good explanation for this. So what this is about, in fact, it's yes. Sorry, someone has a question.
I didn't hear anything. Maybe someone is unmuted.
It was from your group, Robert.
Oh, yeah. Okay, sorry.
Okay. So this problem is a problem of symmetry breaking. Basically, initially you have what is called the racemic state. So that means that you have the same amount of the two enantiomers. So they are represented here with colors. So you have the D enantiomers in blue, the L enantiomers in yellow, and then you have two species which are achiral, A1 and A2. So you assume initially you have a perfect symmetry. This racemic state is thermodynamically the most stable state. And then something happens which destabilizes this racemic state, and only half the species will remain, and as a result, also half the reactions. So we are asking, how can this happen? This symmetry breaking. What is the where does it come from? Okay, so for homochirality, it's important to realize that there are two different aspects. There are two different questions, in fact, in this issue. So the first issue is what is the origin of the initial bias? I mean, between D and L. This initial bias can be small. That's the first aspect of the problem. And the second aspect of the problem is how to amplify and to maintain this initial bias in such a way that you end up with 100%. Because right now, for living matter, we have 100% for all molecules. So these are two different questions. So the question of the initial bias, for instance, is not clear. Depending on who you ask, you may get different answer. For instance, astrophysicists believe that the answer may come from space, that there are in fact evidence that some meteorites, for instance, contain an excess of D enantiomers for sugar molecules, and they expect that there is a bias, a small bias at the level of perhaps our solar system. Okay, so this may well be, but then this is only the question of the initial bias. The problem remains how to explain, how to amplify and to maintain it to a large value. And this, in our view, is only possible thanks to the properties of a non-equilibrium network, which is permanently driven out of equilibrium. And so this proposal, this idea of a non-equilibrium network, of course, is not particularly new. Already in the 50s, chemist Frank introduced such a model. So in the model which is sketched here, you have essentially three species. One D species, one L species, and then one achiral species, which is just A. So you see the model is very simple. You have autocatalytic reactions, which led to an enhancement of the D and the L molecules. And then you have a reaction which is called the chiral inhibition, and which is such that, in fact, the D and the L react together to give back an A. So this is a simple model, which is characterized by this quantity, the enantiomeric excess, which is just the relative dominance of D with respect to L. And the reactions are very simple to write. You can deduce from them that there are essentially three fixed points in this dynamical system. One unstable point, and which is the racemic one, and two stable points corresponding to omega equals 1 or -1, and this corresponds to two homochiral states, one left and one right. So all this is well known, and the only objection we have with respect to a model like that is that it's very simple. I mean, you have only three species, three reactions, and this is maybe not. This is interesting from the mechanistic point of view, but this is a little bit too simple. And in particular, so in our recent work on this problem, we made the following point: is that presumably one can assume that the origin of life may not have started in such a well-defined composition. I mean, we might imagine that it might have started in I don't know, an hot spring somewhere where, in fact, there were a lot of compounds around. It was a kind of messy chemistry. And so we thought that this is an aspect of the problem which perhaps has been overlooked. I mean, the fact that the chemistry needs to be messy, and I mean that the composition has to be complex, heterogeneous. And so we tried.
Sorry, David, can I? Yes? Sorry, Tom posted a question on the chat. So he's asking, in the Frank's model, how are we supposed to imagine that D converts A into D?
There is conversion of D into A. So he's asking
A
about
plus D equals 2D. The same with A plus L equals 2L. So A is achiral. How does a chiral species like D convert a chiral species into its type? Can you put, I guess he's not looking for a physical mechanism. Is it a alpha helix right-handed? How does it interact with a, I don't know, random coil to convert it into a right-handed alpha helix?
Yeah, no, I think it's a good point. I mean, it's I have to be honest. I mean, chemists have been looking for like almost 40 years for a system to realize this. So there are issues. I mean, this is probably one of them, but it's indeed not obvious to see how you can implement this experimentally. And so I will perhaps come to this point later, because I will show you versions of this which actually can be implemented. But this is true that this is not so obvious at this point.
Okay, thank you.
And just a quick question. So A is fixed in your model, yeah? So A is a substrate, or is a, you know, whatever is used to make these molecules, so it's kept fixed to drive it out of a...
No, A is not kept fixed, you see, because we solved the three equations together. It's a dynamical system with three variables.
Okay. Thanks.
Okay, so anyway, so we are there at this this point in the talk. So in order to so essentially what we want to, the message we want to make is that it's the very fact that the system is complex, contains a lot of compounds, which will help this homochirality to emerge. And to prove that, the first step is to understand what is the abundance of chiral molecules in the chemical space of all possible molecules. And if you ask a chemist this question, he would tell you this is kind of obvious. I mean, chirality is kind of rare if you have a small molecule, but as the molecule gets larger, it becomes more probable that it's chiral. It's something that chemists regard as obvious, but somehow we didn't find anybody that actually quantified this effect. And to quantify that, so we just went to chemical database. There's one public one which is called pubchem, which contains quite a lot of compounds, which are reported compounds which exist. And we selected the ones that have less than 21 heavy atoms. That means atoms which are not hydrogen. And we just counted basically what is the fraction of chiral molecules among all these known molecules as function of their lengths, basically. And so if you do that, you see that you have indeed a point where chiral molecules start to dominate over achiral ones. So achiral ones are essentially the blue curves. You have two ways to count them. But no matter how you count them, at some point there are more chiral molecules than achiral ones. And this is something you can do for molecules which are reported that we know exist, but you can also do this in a chemical universe, which is made just by compounds which you have built in a computer. According to the known of rules of chemistry, but you're not really sure that all these compounds exist. You can also do it for a specific class of molecules for which exact calculations are possible. For instance, for alkanes, you can do that. For monosubstituted alkanes, you can also do an exact calculation. And so, in fact, it doesn't really matter which database you use, which detailed molecules you consider. There seems to be always a crossover in a region where molecules are from 7 to 9 heavy atoms per molecules. So it's interesting because this shows that, and it's of course above that you have an exponential increase of chiral molecules. So it shows that in fact there are a lot of chiral molecules, and you don't need to have very long molecules to have this dominance of chiral molecules over achiral ones. Okay, so now that we have this this first point established, so the second point was how can we cook up a model which will end up with a dominance of one of the two enantiomere for all the species involved. And here we know that we need to consider a chemical network which is driven out of equilibrium, and a simple example of that is to consider an open reactor of the type of CSTR, continuous stirred tank reactor, because this is a simple tool that theoreticians have used to study models of this kind. So the dynamics in a CSTR is ruled by this equation, this kinetic rate equation, where you see there's a term that depends on the stoichiometric matrix. So this is the F term. And then there is a term which has to do with the inflow of molecules into the reactor and the outflow from the reactor. So if you do this this approach for large chemical network, you will typically end up with nonlinear equations, but actually what we want to know for this problem is relatively simple. We want to know whether the racemic state is stable or not. And this is a question which you can address within linear stability analysis. So if you do that, you consider this delta x, which is the difference between the left and the right-handed molecules. You will linearize the rate equations about the racemic states, and so in that case the stability of the racemic state will only depend on the eigenvalue of this matrix M. So the rest then is to rely on some tools of random matrix theory. So this is not the first time, of course, that ideas from random matrix theory have been used to study the stability of large complex systems. I think the first person to do that was Robert May in a pioneering paper, which was aimed to study the stability of ecosystems. And the consequence of May's result was, for instance, that he predicted that large ecosystems should be less stable than small ones, and this triggered a debate in the field which lasted many years. But clearly, this was very important realization in the field. So the problem that we have studied is not exactly the same, but this technique is similar. And so to understand exactly how we use it, I just remind you quickly some properties of random matrix theory which are useful. The matrix we need to consider is not necessarily symmetric. So we use the Gierko's circular law for matrices whose entries are real, IID distributed, with mean 0 and variance sigma square. In that case, the eigenvalues fill a disk which grow like the square root of the size of the matrix in the large n limit. Then, if you assume that the elements have a non-zero mean, in addition to the circle, you will have an isolated eigenvalue, which typically is of the order of mu times n. So it's generally a much well separated from the circle, and it is relevant to the stability when mu is positive. When mu is negative, of course, then it's not relevant because you are interested in whether there is an eigenvalue with a positive real part. Okay, so with these two results in hand, you can understand that there will be two instability mechanisms depending on whether the edge of the circle reaches the y-axis, or whether this is the isolated eigenvalue, which some people call the outlier, that does reach the y-axis first. But whether this is one or the other, in any case, as the system gets large, you will have this transition. So this is, as you can see, this is a very general argument. You may think this is completely disconnected to reality in some sense. It's very fundamental, and it's not obvious to see the connection with the dynamics. For the simple reason is that you can have many dynamics which will have the same Jacobian matrix and therefore the same stability condition. In order to propose this as a mechanism, so we had to show that it was possible to find dynamics which would indeed satisfy this general principle. So to do that, to cook up a dynamical model, we started again from the original Frank model, except that now we are multiplying the number of species so that we will have something like a large matrix that will rule the stability of this generalized Frank model. So you see, so I have now multiplied the species D and L. I have a D index I and L index I. In this case, I only keep one achiral species. We have also considered the possibility to multiply them as well. And we have rate constant, which we will take as random numbers. And they are displayed here in this set of equations. So when you simulate this model, you see that indeed, depending on the condition, you may have all the species, the D and the L, which go to 0, or you have possibility of an homochiral transition in which certain species will disappear at the benefit of others. And typically, this happens above a certain value of the A0. So the A0, if you remember, this is the threshold of the injection of the A molecule in the system. So here we assume that we inject only achiral molecules so that we don't break the symmetry from the molecules that we inject in the reactor.
So quick question. Sorry. So this is a so now there must be some motivation, and you mentioned some motivation. Can you come back to Tom's question now, because now you've got a universal achiral substance that can be converted into many different chiral.
Yes.
So what physical systems would that represent?
Yeah, so the difference with respect to the original model is that now you see that the one molecule I is not involved in the replication itself directly. So you don't have a DI gives back to DI. In fact, it appears that now what is important is the fact that it's collectively performing autocatalysis, not directly at the level of a single reaction. So that's the first point. But regarding the question of what is A doing in this model, so here it's important to have a certain property for this A molecule. So the A molecule has a high free energy in this model.
So I guess that's not my question. I can see it mathematically. But I guess what physical substance, what physical material would that represent? So Tom in the chat said, can it be some sort of functional groups replacing an H with a CH3, for example? Is it something that you imagine when you cooked up this model? I mean, it's not. Is it peptides? Is it DNA that's being made into?
Yeah, in the last part, I will propose a model which is more precise in the sense that it is connected to the formation of a polymer, and then you have something like template directed polymerization. I mean, you see things a bit more clearly. I mean, here A can be essentially any fuel molecule. The important point is that this is bringing some energy into the system. This is feeding the autocatalytic cycles, because in general, this autocatalytic cycles, they must be fed by fuel molecules, which are consumed. And these high energy molecules are turned into low free energy molecules, which are represented here by this A tilde. So it's true, I don't have a very, I mean, I don't have a very clear idea of what this A could be, but this is clearly a high energetic species. That's all I can say for the moment.
Yeah. But since you said that you will map it onto some sort of polymer templating, but that's just copying a 0 or 1 digit. It's not really chirality in the sense of a mirror image being broken, right?
Yeah, well, you'll see. I mean,
okay.
You know, yeah.
Sure. Sorry.
Can I just ask something very briefly?
Yeah, sure. Go ahead.
So here you separate left-handed and right-handed. So in the end, you want a scenario where you only one of the type of chirality survive. But in nature, you have amino acids and sugars which have opposite chirality. Is it right?
Yes.
So you have these mixed states. But I suppose depends on your inhibition law, I suppose.
Yeah, and this is very important. And I think this is the strength of this model, is that we can explain the fact that different molecules can end up having different handedness in the end. And this is fine. Because what we need to explain is that there's dominance of one of the two enantiomer, but it doesn't need to be the same for everyone. That's a very important point. I will come back.
Okay, thanks.
Okay, so for the generalized Frank model, you can work out the Jacobian matrix. You can analyze it with the standard method, and you find that the threshold obeys this condition. And basically, this means that you have a diagram of this type in terms of the A0, so the injection of energy in the system, and NC, the number of species. So if you start in the red region, you are in the racemic phase, and if you increase the number of species, so you will move horizontally, and at some point you will end up in the homochiral phase. If instead you decide to drive the system harder, inject more energy into the system, then you will move vertically, but you will also eventually end up in the homochiral phase. So this is the idea. You can prove that also by looking at the probability for this instability to happen as function of the threshold, and you see that the crossover becomes sharper and sharper as the system size increases. Now, at this point, you may ask, okay, this is a dynamical model, which indeed satisfy the prediction from the random matrix argument, but is it really reasonable to treat this chemical network as a random matrix, or at least the Jacobian of this chemical network as a random matrix? Because in the random matrix argument, you need that the entries need to be IID and so on, and it's not obvious that this will be the case in the chemical network. And so, in fact, to check that, we just looked at the spectrum of the eigenvalues in this generalized Frank model, and we find that these eigenvalues typically do not fill a circle, and that's because there are correlations in these eigenvalues. So this is not the simple model of IID entries doesn't work. But it doesn't matter for the general argument, because you will still have the outlier, the isolated eigenvalue, which will nevertheless dominate with respect to cloud of eigenvalue, which may be deformed by correlations. And in fact, in complex ecosystems, we know this that interactions typically lead to correlations, and which deform the circle. So this is a similar idea here, which is happening at the level of a molecular ecosystem in some sense. Okay, so now to come back to your question regarding the sugar and the amino acid, and this is where also you see the difference between our problem and ecosystem, because of course this problem has a specific symmetry between the left and the right, which typical ecosystems don't have. So there is a symmetry in the matrix. If you do a permutation of one enantiomer with its partner, you can look at this transformation. You will see this will not change the eigenvalues. So in fact, this is a good news, because that means that you can change the conventions. You can decide to assign the D and the L in a different way. This will not change the result. This is good news, because we have different, in chemistry, different ways to measure chirality, and they are not really consistent with each other. I mean, you may have, for instance, the rotation of the plane of polarization, or you may have another definition based on the groups of molecules which are involved. And these two definitions typically don't coincide. So this is fine. And this is also fine to have different groups of molecules have different signs for the same reason. And so we have a discussion about this, and there is no need of a global sign, and it's at the same time we suggest that it's not, of course, randomly that probably the amino acids and the sugars decided to have different signs. Probably the reactions they are involved in work better when this is that way. So there is something here to be studied more generally, namely the evolution of the signs within different classes of molecules. Okay, so then quickly, so the other point that we addressed is, of course, this random matrix argument. You may have the impression that it works for any fixed point, and then what about the homochiral fixed point then? So if it was working there, it would be also unstable, and then you would have a problem. But in fact, it turns out that this doesn't happen. At the same time as the racemic become unstable, the homochiral state becomes stable, and so in fact everything works out in the way you would expect when you study the stability of all the fixed point. This approach is also interesting because you can introduce effects due to sparsity, and this is also something Robert May had pioneered, because sparsity will essentially affect the radius of the cloud of eigenvalue, and so you can understand how this effect will scale essentially. You can understand the modification of the threshold that goes from this effect, and you can discuss the effect of sparsity at the level of all the species of the network, but you can also choose to have sparsity only for the specific autocatalytic reactions, for instance. And so you can, we have then studied the separate effect of that form of sparsity as opposed to the other one. But let me just skip that and just summarize this second part on the random matrix approach to homochirality. So you see the strength of this approach is that
it provides a robust mechanism, because random matrix theory is of course a theory which has universal consequences, and so this suggests that perhaps we have a way to explain this robustness, which is important when you want to discuss the appearance of homochirality in a very heterogeneous environment. This framework can account for different classes of molecules having different handedness, and it can be dynamically realized in practice, so this is important. And the symmetry breaking doesn't need to involve very long molecules, only relatively modest one, about 9 heavy atoms are enough. Okay, so this ends my second part, and I have just one last part to finish. Are there any questions for the second part? Okay. So then in the last part, so I will try to establish a link between the emergence of homochirality and the emergence of the first polymers. And to do that, so there are different questions that need to be addressed. Of course, it's a big issue. So you would like to know what type of polymerization are you talking about? Is it random polymerization, so in a simple in a single strand, if you want, or is it important that the polymerization is template directed? Other questions are, what are the chiral interactions? Do you need specifically selective chiral interactions, or can it work also when they are not selective? What about racemization reactions? So if you don't know what racemization reactions are, I will explain in a moment. What is the role of surface, and so on. So there are many issues. So in order to start with this, so we started with the first question. So is it important that we have a single polymerization or template directed polymerization? So to address this question, we started by considering some random polymerization. So this is, for instance, a simple model that can do it. So you have the two types of monomers. You can think of them as being, for instance, the left and the right monomers, and you have reactions where they can be added to form longer oligomers, and they can be cut. So you can look at this as a simple equilibrium like this. And then racemization reaction are reaction that can turn the D monomers into L monomers. So this is of course a very simple model. As you can guess, this simple model will not be probably enough. But what happens is that you can imagine that, for instance, if you started a polymer with left-handed monomers, if a right-handed monomer comes, then perhaps its addition will be slower, and this would mean that you have a bias then in the polymerization. This can be an important ingredient, and typically this ingredient can be tuned by the presence of a surface, because if you have a surface that can cause this kind of bias in the rate constant. So this is basically the simplest model you can cook up for polymerization. So if you don't have racemization reaction, typically if you look at the fraction of homochiral strands, they will decrease exponentially as function of the length. I mean, clearly, if you want to have a perfect homochiral strand and you have two possible handedness, well, I mean, this probability will go as 2 to the will decrease exponentially in k, and the length of the polymer.
So this corresponds to the white solid line. So this is just exponential decay, nothing very interesting. If you increase the bias or the chiral selectivity, you can also increase the fraction of homochiral strands, but the pool is still racemic, so you're not really achieving what you want. Now, if you have a racemization reaction and a closed system, this will help you because as soon as you start to build some homochiral polymers, there will be a depletion of the corresponding monomers in the solution. But thanks to the racemization, you will be able to overcome this depletion, and therefore you will get to a higher level of homochirality. So this works. These curves show that enantiomeric excess as function of time can reach a finite value, non-zero value, and this shows that in some sense you solve the problem that you can get some homochiral polymers. The problem is that the excess, the enantiomeric excess that you can get in that way is still relatively small. So it's just only a few percent. So we're not really going very far with simple polymerization. We are certainly not able to reach the 100% homochirality that we see today. So it seems that there is not really a choice. We need to go through template-directed ligation. So then we need to consider something like that. So we have the addition of monomers on a copy of the template. So this happens with rate k on and k off, and we have also rate of ligation of these oligomers, which are bound to the template. So we form this duplex, and this duplex can be separated. So we don't really go into the details of what can cause that, but we know that if there are, for instance, day-night cycles, change in temperature, for instance, we can separate the two strands, and this can then start over again. And then we may have also racemization reaction. So this racemization reaction, perhaps they look strange to you. But in fact, they are not so unusual, especially in the context of prebiotic chemistry, because typically you will have high energy species. This is also something that came up already in the talk, but you can imagine, for instance, that you have UV lights, and typically UV lights will produce free radicals, and these free radicals are essentially achiral molecules. So simply thanks to UV light or thanks to high energy molecules, you will be able to racemize systematically all the chiral centers of a molecule, even without enzymes. So this part is not a problem. So let's look into more details how to make this model work. So we need to describe the energetics of the addition of monomers to the template. And so if we only take into account, I would say, the vertical interactions, this will not be enough, because you can imagine that nearby monomers will also matter energetically. And so we found that indeed you have to take into account vertical and lateral interactions. So here in this simple model, we have these two parameters which describe these two interaction energies. So then you calculate the overall hybridization energy thanks to calculation of block energies, and this can be done also with experimental data. It's possible to make amino acid with left or or write monomers and to measure the change in the thermodynamic parameters so as to determine the U and the V. Now the legation. So that's where it becomes important to understand the following effect, which is called the chiral inhibition. So you see, we use the same terms as in the Frank model, even though this is quite different. But you will see that, unlike what was going on in the Frank model, this is actually experimentally, this is an experimental fact that such an chiral cross inhibition exists. So what is chiral cross inhibition? So imagine that you're adding, you're trying to ligate an oligomer which has the same handedness as the template. Then obviously this is quite efficient. But then if you have added a wrong monomer and you still want to perform ligation, then this ligation will be much more slow. And this is being observed already by Joyce in the 80s. So this means that in that case, the ligation is reduced by this parameter sigma, and the smaller the sigma is, the larger this inhibition is. So all these effects will be important. So now we simulate this block energy model, and we start with the case that there are no Rasterization reactions. On the left, you see a figure for the fraction of homochiral motifs as function of time. And you see that if you have a large inhibition, so this corresponds to the red case, the fraction of homochiral motifs, oligomers, if you want, is much larger. So inhibition really helps you significantly to increase the fraction of homochiral strands. So that's the first point. Precise values of U and V are not critical. We have tried that. They don't affect essentially this. They don't change very much this effect I'm talking about. So in other words, the thermodynamic bias due to this stacking energy is not enough. Chiral inhibition is really important for this problem. But now you may think that you have solved the issue, but in fact it's not completely true, because if you look at what is the state, the chiral state of these oligomers, in fact you realize quickly that you are forming essentially very short polymers. They are homochiral, but they are mainly dimers. So this is shown here with the fraction of the strands as function of a parameter which measured the homochirality. So when it's 0, then you have a racemic state, and you see. So if you consider oligomers which are rather long, you have a distribution which is completely symmetrical, and that means that essentially the long polymers are not homochiral. So this works to some extent thanks to inhibition, but you're still not exactly achieving full homochirality of long polymers. So if you want to achieve that, you need to have everything. In other words, you need to have the block energy model with now Rasterization reactions and chiral inhibition. So on the left, you have the enantiomeric excess, and on the right, you have the average length as function of time. And you see, for instance, with the curve on the left, that again, you have a much stronger effect when you have large inhibition reaction. And this effect manifests in first the fact that you reach a certain plateau relatively quickly, and then after that plateau, you have a second growth phase which is very slow. So the first plateau corresponds to a steady state that is already also present in the absence of rasterization. So in the previous case. So this, in fact, this curve, you have exactly the same in the absence of rasterization. So the rasterization really is responsible for the second phase, the second growth phase, the one that leads to a full homochirality. So what is interesting is that once you are in the second growth phase, the average length is significantly increased, because this is what you have at the end of the first phase, and you see that the second phase allows you to reach longer polymers, and they are perfectly homochiral at the end. Okay, so and here I'm just pausing to say, okay, perhaps this is important because we may regard this as a mechanism to boost polymer lengths. And in the literature, this is known to be a problem. I mean, in the origin of life research, people have been struggling to find ways to replicate long polymers, especially without enzymes. And this may be one of the ways to do that. And what is interesting is that, in fact, it works because of inhibition, and this is in some sense amusing that, in fact, it's the very effect that people thought would be a block, a bottleneck into origin of life, namely this chiral inhibition, which in fact is making this homochiral transition possible. So just one word about this problem of the lengths. I mean, of course, this is connecting to much older work, the work of Eigen, who derived this replication error threshold, which probably you have heard of. This is a threshold which constrains the length of the polymer that you can replicate with the accuracy of the replication system. And this is a major constraint in origin of life scenarios. And for many years, people have tried to find ways to get around this error threshold. And for instance, in the 80s, a stochastic corrector model was proposed, which is based on a transient form of compartmentalization. And in this way, you can overcome this replication threshold. In fact, so we were inspired by this work, and also by an experiment which confirmed this in a microfluidic device carried out in 2016. And so we have studied the effect of transient compartmentalization on getting around this replication error threshold. So it's interesting that now, in some sense, the homochirality adds another layer to this, in the sense that we can also get to longer polymers by a different mechanism that doesn't require transient compartmentalization. I think it's about time for me to wrap up. So in this last part, I try to link so the emergence of homochirality with that of the first polymers. We may have found a mechanism that favors the formation of long polymers. In principle, this could work for nucleic acids, but this may also work for polypeptides, and that would be also quite important. Basic effect is that by reducing the chemical space, so because in fact you're giving up half of the possible molecules due to homochirality, you specialize yourself in one handedness. You may look at this reduction of the chemical space as producing a kind of lowering of the entropy of the sequence, and it seems that as a result of that, you can reach higher selectivity and perhaps the emergence of a new function. And so this is interesting that, in some sense, the same mechanism that explained the emergence of the first polymers may explain also the homochirality, and may be also connected to the emergence of the first catalyst, and therefore, in some sense, there's a competition. I mean, there's yeah, no, there's a synergy between different effects which all contribute to this scenario in the origin of life. Okay, I hope you. Thank you for your interest, and I'll be happy to take some questions.
Thank you so much. Oops. Thank you very much for your talk. Very stimulating. Let's see if there are some questions. So in the chat box, it's mostly what Tom wrote. He left now already.
Okay.
But I guess he was very interested in the mechanism, how to change the chirality. So basically that's what you discussed at the end, right? Sort of the block Rasterization, essentially, where you have longer stretches of a polymer changing the chirality. Is it right?
Yeah, that's right.
So could this be done, for instance, if you have a DNA which is has a certain handedness? Could you then essentially one mechanism could be to unwind the molecule, and if you have two stable configurations, which is not the case in DNA, unwinding and then changing the conformation based on it.
Yeah, I'm not sure you necessarily need to unbind DNA, but what you need is to have the left and the right monomers, and that we already have for DNA. But if you want to do it with modern techniques, I mean, we lack the enzyme that would perform the polymerization for the other handedness. But this is something that can be sorted out. I mean, in fact, some people have already essentially achieved that step. So as long as we have different monomers that we can make directed polymerization, whether we use enzymes or not, we have everything we need. We don't need to unwind anything.
Okay. Yes. Yeah. I'm just because also in DNA there are different conformations. You know, DNA, B DNA, Z DNA, I think, and it depends on humidity, sort of physical parameters, effectively salt concentration, temperature. What else was there? Physical stretching of the DNA. Yeah, but anyway, so that was basically where you don't necessarily need an enzyme. You can do sort of physics. But there's Javier or Xavier has raised his hand. Do you want to just unmute and ask your question?
Yeah. So I wanted to ask about the last slides about the compartmentalization and selection methods. So what will it be a selection method, for example, for a specific enantiomer? Just the polymerization rate, or because you will have to select the entire, let's say, compartment. I'm right?
Yes, you can. I mean, yeah. What I was talking in this last slide is absolutely a selection at the level of compartments, and that's how it works. This transient compartmentalization. I mean, you perform selection at the compartment level, but with chiral things, I mean, it can totally make sense, because we know that, for instance, with coacervates, you can have compartments which have a well-defined chirality. So, I mean, molecules will phase separate according to their chirality. So you have the possibility to do a selection of compartments thanks to chirality. Exactly.
Okay, many thanks.
Thank you.
Okay, let's see if there are any more questions. Okay. Yeah, so currently there are no more questions. Yeah, so I guess we give you some rest. Thank you so much for joining us and your stimulating talk, and yeah, hope to see you soon, maybe even next week in London.
Exactly. I'll let you know. Thanks a lot for joining and for all these very interesting questions. Thank you.
Thank you. Bye everyone. Thank you for attending.